Hello, my name is James Treveri, and I'm presenting on behalf of Team 55 for the Fall 2020 CSE6250 course project. In what follows, I'll highlight the approach we use to predict the length of stay for ICU patients. Hospitals are continually on the lookout for ways to allocate resources with greater accuracy and efficiency, and have invested in methods to assist in scheduling elective admissions, predict bed needs, and measure hospital bed utilization. In a similar vein, hospital administrators need to have the ability to accurately predict how long a patient will stay in the ICU and need to develop an understanding of the factors that influence a patient's length of stay. One of the interesting aspects of hospital ICU prediction is there is no clear consensus preferred approach. Methods as varied as ARMA time series models, Markov chains, skewed exponential family GLMs utilizing a Tweedy gamma or inverse Gaussian response, and variations of regression trees have been employed with varied degrees of success. The primary question we're hoping to answer is how can we better understand the remaining length of stay for ICU patients 48 hours after admission? We will survey a number of different modeling techniques and approaches to try and come up with the best method. And because tree-based regressors are relatively simple, transparent, intuitively explainable models that also serve as the starting point for more complex algorithms such as AdaBoost and gradient boosting, and also due to their frequency of appearance in the existing literature, we've decided that the decision tree regressor will be our benchmark model. Our primary data source was the MIMIC3 database, which is the integration of de-identified comprehensive clinical data of patients admitted to the Beth Israel Deaconess Medical Center in Boston, Massachusetts between June 2001 and October of 2012. It is comprised of over 53,000 adult patient ICU stays. The MIMIC3 database is made available to researchers around the world under a data use agreement. Here we have our initial model results. For context, mean length of stay for training data was about 8.7. As we could see, all the models performed quite poorly. Our MSE of 10.7 for response having a mean of 8.7 is unacceptably high. We reviewed these results, it felt as if our models were missing something fundamental. After reevaluating our approach and taking another look at the available data elements in MIMIC3, decided to focus on how a patient's ICU stay ended. As a simplifying assumption, we hypothesized that a patient can leave the ICU in only one of two ways, either as a consequence of healthy recovery or as a consequence of death. Since the mortality status of a patient is available in MIMIC3, we can compare empirical quantiles of patients that die versus patients that recover. They're different enough, it might be worth somehow incorporating that information into the next generation LOS model. In this slide, the top histogram represents the empirical distribution of length of stay for patients who left as a consequence of recovery, and the bottom, those who left as a consequence of death. Values up to the third quartile are in the same ballpark. When we get into the tail, we see a large discrepancy in the 95th empirical percentile, where healthy recovery LOS is 32.18 versus 23.42 for non-living patients. We concluded that this difference was relevant enough to warrant further consideration. The question then becomes, how to account for patients living in non-living status at the point of prediction, just 48 hours after admission. Our approach employed a two-point mixture model, which is built as follows. On the full training cohort, using mortality status as the target, fit a classifier to estimate the probability of leaving the ICU as a consequence of death. Divide patients into two subcohorts based on mortality status. Fit two separate regression models using length of stay as the target, conditional on mortality status. The final length of stay estimate on holdout will be represented by this expression below, which is a weighting between the alive and dead regression models with the probability of death as the weight. Note that the decision tree regressor metrics represent results from the original all-in model. This allows us to quantify to what degree our second generation models improve upon the initial approach. We see some improvement relative to our benchmark in terms of R-squared, but for the other metrics it's hit or miss. If we perform a side-by-side comparison of similar models across first and second generation, vary. The gradient boost model performed slightly better across all metrics, but the multi-layer perceptron performed worse. The fact of the matter is that even with mixture model implementation, our MSE is still way too high. Another thing to note is that summary metrics are useful, but they don't tell the whole story. It's generally more important to assess how well the model differentiates between the smallest and largest values in the target response. And this can be accomplished with the aid of a lift chart, which is also called a quantile. Lift charts are constructed as follows. We arrange the data based on actual length of stay from smallest to largest. We then bucket the data into quantiles, such that each quantile has the same number of records. Within each bucket, we then calculate the average actual and predicted length of stay. Doing so, here's what we get. Two things to keep in mind when using lift charts to assess model adequacy are: one, predictive accuracy. How well does the model predict the actual length of stay in each quantile? Our models are higher than actual on average in quantiles 0 through 7, and then too low in the two rightmost quantiles. It may be that the results are highly leveraged due to outliers, and that those outliers are having a high degree of influence on the overall fit. Another thing to look at is vertical distance between first and last quantiles. First quantile contains patients the model believes will have the briefest length of stay. The last, those patients that will have the longest length of stay. Although the discrepancy between actual and modeled length of stay is large in the rightmost bucket, the trend is going in the correct direction. It's just not getting there fast enough. In conclusion, we found that the 2-point mixture model did offer some improvement over our original all-in approach, but outliers may be contributing to the poor fit. It may be worth considering censoring length of stay at some predetermined threshold to remove those outlying observations and train the model on that censored data set. In addition, we want to consider incorporating additional severity scores into the model and remove our simplifying assumption and instead consider a K-point mixture model, which considers an array of possible outcomes of leaving the ICU. We could always engineer more features, and we could work closely with medical professionals to gain a deeper understanding of the primary drivers of LOS. Thank you for your time. Hope you enjoyed this presentation.